Hey everyone, welcome to another deep dive. Today we are going to be diving into the world of number systems.
Yeah, number
It's going to
systems.
be a wild ride.
Buckle up.
So our main source material for this deep dive is this textbook chapter on number systems. And, at first glance, it might seem a little dry, but trust me, within these pages are some seriously mind-blowing concepts just waiting to be unearthed. I'm excited to unpack this with you.
Yeah, it's easy to take numbers for granted, right? I mean, we use them every day.
Totally.
But taking a closer look at the systems they form, well, it reveals a whole new layer of appreciation for how math works. At least for me, it did.
Absolutely. I couldn't agree more. So to get us started, let's imagine we're taking a stroll, a mathematical stroll, if you will, along this infinite number line. We'll begin in a place we all know, a comfortable starting point, the natural numbers. 1, 2, 3, 4. You get the idea. The ones we use every day for counting. And mathematicians, they love their symbols, so they represent these natural numbers with, you guessed it, the letter N.
Of course, N for natural numbers. Makes sense.
That makes total sense. But hold on a second. What about 0? Zero's got to be in there somewhere, right?
Oh, yeah, 0.
Yeah.
Well, zero has to be included too, of course. When you add 0 to the mix, you get the whole numbers. And those are represented by, get this, the letter W.
W. Okay. I like it.
And as we venture further down this number line, we bump into the integers.
Integers.
Represented by, and this is a bit of a curveball, the letter Z.
Z. Why Z?
Well, it comes from the German word zahlen, meaning to count.
Ah, okay. I was not expecting that.
And the integers, well, they include those positive whole numbers we were talking about, along with their negative counterparts.
So we've got these fundamental sets now, N, W, and Z. They're like the bedrock, the foundation upon which so much of math is built.
Exactly.
But here's where our textbook throws us a bit of a curveball. It asks this question: can every single number on this infinite number line, every single one, be expressed as a fraction? What do you think?
That is a great question. And it might seem like a simple question, but it leads to a pretty fascinating realization. And that is that the answer is no. Not all numbers can be expressed as a fraction. There are numbers that exist outside the realm of those neat and tidy fractions.
What? Okay, hold on. So there are numbers that can't be expressed as fractions.
Yep, that's right. These mysterious numbers, my friend, are called irrational numbers.
Irrational number. Okay, now we're talking. Tell me more about these irrational numbers, these rule breakers.
Well, what makes irrational numbers so fascinating is their inherent complexity. They're like the rebels of the number world. Unlike rational numbers, which can be neatly represented as a ratio of two integers, irrational numbers, they can't be. They're decimal expansions. Well, they go on forever, without ever repeating, creating these endless, unpredictable sequences.
Whoa. Okay, so it's like if we zoom way in, like way in on a rational numbers decimal expansion, we're either going to hit a dead end or we're going to find ourselves stuck in a loop, right? Going around and around forever.
Yeah, exactly.
But with irrational numbers, it's like we're venturing out into this uncharted territory. There's no end in sight.
That's a great way to put it.
Now, the textbook also mentions this. It's kind of a wild story, actually, about the Pythagoreans, those ancient Greek mathematicians.
Oh, yeah, I've heard of them.
They were supposedly horrified by the discovery of irrational numbers. Can you imagine a mathematical concept so groundbreaking, so earth-shattering that it could shake the very foundations of your understanding? That's wild.
It sounds a little dramatic.
A little bit.
But it speaks to a real change in how they viewed math. You see, the discovery of irrational numbers like the square root of 2, it challenged the prevailing belief that all numbers could be represented as simple fractions. It was a big deal.
It totally was. And speaking of numbers that defy easy categorization, we can't forget about pi.
Pi.
The textbook mentions how ancient cultures, without our fancy calculators and computers and stuff, had these surprisingly accurate approximations of pi. It's amazing what they were able to achieve.
Oh, absolutely. It's a testament to human ingenuity, for sure. Take the Silpa Sutras, for example. They were a set of Indian mathematical texts, really old. And they had these methods for calculating pi that were incredibly close to the methods we use today. It's incredible.
It really is. And now, with our modern tools, we've calculated pi to trillions of digits, right? And yet it just keeps going, this never-ending, never-repeating decimal.
It's wild.
It just makes you think, even with an infinite number of digits, we can still approximate and use pi effectively. It's a testament to the power of mathematics, to its ability to represent the world around us.
Couldn't have said it better myself. It's like we're harnessing infinity.
It's like pi is a perfect example of order and chaos all wrapped up in one little symbol.
It really is fascinating. And you know what's really interesting is how we can work with these irrational numbers, these numbers that seem to go on forever. But let's get back to our number line journey, if you will.
Okay, back to the number line.
As we keep exploring, we start to see that this difference between rational and irrational numbers, it's not just some theoretical thing, you know. It actually has real implications for how we work with numbers in practical ways.
That makes sense. So how do we wrangle these irrational numbers? What tools do we have at our disposal? I know our textbook mentions something called rationalizing the denominator. What is that?
Okay, so imagine this. You're working on a math problem, and you need to express an idea in a way that's easier to work with, right? Even if the value of the expression itself doesn't actually change. That's where rationalizing the denominator comes in.
Okay, I think I'm following. Give me an example.
Sure, take the expression 1 divided by the square root of 2.
Yikes. That looks a little messy.
Yeah, it's not the prettiest thing,
Yeah.
but we can actually simplify it. And we can do that without changing its fundamental value.
Okay, how?
By multiplying both the top and the bottom, the numerator and the denominator, by the square root of 2.
Okay. And that gives us...
Square root of 2 over 2, it's still the same number, just expressed in a way that's easier to handle.
It's like we're giving that irrational number a bit of a makeover, making it more presentable, more manageable.
Exactly. And this technique, this rationalizing the denominator, it's super useful as you get into more advanced math where irrational numbers pop up all the time.
So we're learning to coexist with these irrational numbers, finding ways to work with them despite their infinite nature.
Precisely.
Speaking of things that seem infinite, let's talk about those laws of exponents we learned back in school. You know, like when you multiply exponents with the same base, you just add the powers together.
Oh, absolutely. Those laws are fundamental.
But here's where things get interesting for me. Our textbook, it asks this question. Do these laws still apply when we're dealing with, wait for it, fractional exponents?
Ooh, fractional exponents. See where you're going with this.
Like, what does it even mean to raise 2 to the power of 13? It's like we're breaking the rules of exponents, pushing them further than we thought they could go.
It does feel that way, doesn't it? But the amazing thing is, they still work. We can actually expand our definition of exponents to include these fractional powers.
So how does that work with the 2 to the power of 13?
Well, think of it this way. When we see 2 to the power of 13, what we're really asking is, what number, when multiplied by itself 3 times, equals 2? We're essentially working backwards from what we know about exponents and thinking about roots in a new way.
So the cube root of 2 is like the answer to that question.
Exactly. The cube root of 2, which we can represent as 2 to the power of 13, perfectly captures that idea.
It's amazing how these rules of exponents, which can seem so abstract at first, have this incredible flexibility. It's like they're revealing new ways to express mathematical ideas.
That's the beauty of mathematics, isn't it? These systems we've built, these rules we've discovered, they have this remarkable ability to adapt and expand as our understanding grows.
It's like we're constantly pushing the boundaries of what we thought was possible within these mathematical systems, and they just keep surprising us.
And what we've explored today with these different types of numbers is just a small glimpse into this vast and intricate world of number systems. From those simple counting numbers we all learned as kids to these boundless irrational numbers, each type of number has a crucial role to play in how we understand mathematics.
It really makes you appreciate how these concepts, which might seem abstract at first, really underpin so much of how we make sense of the world around us. Whether we realize it or not, we're surrounded by these mathematical systems every single day.
Absolutely. The patterns we see in nature, the technology we use every day, even the fabric of the universe itself, it's all connected to the language of mathematics, and number systems are the foundation of that language.
It's incredible. So the next time we see a number, whether it's a simple fraction or a decimal that just keeps going and going, it's worth taking a moment to appreciate these intricate systems that those numbers are a part of.
Because even a little understanding of these systems can give us a much deeper appreciation for the beauty, the order, the sheer elegance of mathematics.
I completely agree. Well, that's all the time we have for today's deep dive into the world of number systems. Until next time, keep exploring, keep asking questions, and keep marveling at the wonders that are hidden within the world of numbers.